Multivariate linear regression derivation. In the previous lecture, we had seen how to do derivation in case of univariate linear regression. That is the simplest case of linear regression. Specifically, we had considered only one independent variable and also one dependent variable. That is what we did in the previous lecture. It was something like this: y cap is equal to w0 plus w1x. So you had derived something like this, where y cap is the predicted value, x is the independent variable. So given a value of x, we had to find the value of y cap, and we had the value of y, which is the actually observed target. Then we compared y cap and y, and that is how we did the derivation. So in this particular lecture, instead of this single y and single x, we'll be having multiple variables for y as well as x. So conceptually, if you think, it is like this. Here we had only one feature. So if you are analyzing some problem, as an input, you only provided one feature. This time, you will be provided multiple features. There will be features x1, x2, x3, and so on. All these features combinedly contribute towards finding the value of y. And similarly, in case of a single y, this time you will have to find multiple y's. There will be y1, y2, y3, and so on. So there will be multiple y's and multiple x. In practical scenarios, when you solve some problem, you may encounter situations where there is only one y but multiple x's. So once you understand the derivation we are going to do now, you can simply substitute 1 in case of the m that we'll take for y, and you can solve it for single y as well. That's simple. In the previous lecture, we took the simplest of the cases for linear regression, and in this lecture, we are solving for the complex case of linear regression, in which you have multiple variables for x and y. Let us first understand this, how the equations will be formed, and then we'll use matrices in order to do the derivation. So the whole idea is, in the previous lecture, we did the derivation directly from the equations using the variables, and this time we'll do it using matrices. So I want you to understand how to solve it using the variables that we did in the previous lecture. And in this lecture, I want you to understand how you deal with matrices. So the equations will look like this. Let us say you have a y0, or let's say we'll start from y1 only, y1, which will be something like w0 plus w1x1 plus w2x2 plus w3x3 plus so on, right? Let us say you have some 5 or 6x. Then it will be w4x4 plus w5x5. So this is how your y1 will be formed. Similarly, your y2 will be formed with a different set of w's. So what I'll do is, I'll mark this as w10, w11, w12, 13, and so on, so that you can differentiate. For y2, you will have w20 plus w21x1 plus w22x2 plus w23x3 plus so on. And for y3, how will it be? Now you can understand it, right? It will be w30 plus w31x1 plus w32x2 plus w33x3 and so on. So what you have to understand is, the value of x1, x2, x3, etc. that you use will be same for derivation of y1, y2, y3 and whatever. Whatever be the number of y's you have, for all those, you will have the same set of independent variables x1, x2, x3. If you see, the same x1 is used in the derivation of all y's. What changes? The value of w changes. So in the previous derivation, when we did, you had only one w0 and one w1 to find out. But in this case, see then how the number of coefficients is increasing. You have w10, w11, 12, 13, then you have 20, 21, 22, 23. So as the number of independent variable increases, the number of w's will increase. Similarly, as the number of dependent variable increases, there also the number of W's will increase. In fact, it will multiply. So we are dealing with matrices because the number of W's that you want to derive, that will be huge. Previously, we were able to identify W1 and W0 separately because there were only two W's. But here you're having to deal with all these W's, right? All these are your different coefficients. So if you solve for each of them, that will take a lot of time. Instead, when you do matrix operations, what becomes easy is this whole thing will be populated in a matrix. So with a simple matrix operation, you will be able to find out the values of all these W's. So this is the idea behind usage of matrices for multivariate linear regression derivation. And again, remember, if you have only one y in your derivation whenever you're solving a practical problem, you can simply take a single dimensional matrix instead of the multi-dimensional matrix I'm taking. I'll be taking a two-dimensional matrix. You can take a one-dimensional. So it is easy. If you understand what I'm going to do now, you can solve for any linear regression. Okay. So let us start. You just keep this thing in mind, how different W's, X's and Y's are related. Once you have this thing in mind, it will be very easy. Okay. So let's start. Let me erase all this off and we'll start with the derivation. So before we start with the derivation, you need to be very clear with all the variables we are going to use, all the dimensions of each matrix. See, whenever we are dealing with matrices, you need to know the dimensions of each matrix. You need to understand why each matrix is of what dimension, and then you need to understand how we are going to do mathematics with it. So the first thing you have to know is that we are having n data points. N is the total number of data points that we have. So we'll have x1, x2, x3 and so on. Such n different sets of x's you will have. So you have to find y from x, okay? You have to find y from x. So when I write x and y here, it is not a single value. This x includes x1, x2, x3 and so on. Similarly, this y includes y1, y2, y3 and so on. So each value of x, you have to find a value of y. So again, remember, each x is composed of multiple x's, which is x1, x2, x3, so on. So there will be n such data points, 1, 2, 3, 4, such n different data points is what you have with you. So that is n, okay? The next thing is that you need to understand the dimensions of each of the matrices. Previously, in univariate, we had written the equation as y is equal to w0 plus w1x. This, instead of this time if we write like this, it will be very large, because in the previous, just before this, I had shown you that y1, y2, y3, for all those you will have to write different equations, and each equation will be very large because you have multiple values of x. So instead we'll be using matrices here. You'll be writing it as y. So capital always denotes matrices and small letter denotes normal variables. That's how we'll deal with this. Y is equal to x w plus epsilon. So here this x is the matrix which includes all the values of x. This w is the matrix which includes all the values of coefficients, that is w1, 0, 1, 1, 1, 2, etc. that we saw in the previous slide. And this y, this is the matrix which includes the values of all the y's. And what is this epsilon? Epsilon we are adding as an error term. That is, when we are calculating y is equal to xw, it won't be exact. There will be an error that happens. The value of xw won't be exactly equal to y. Instead, there will be a slight error. That error we are denoting by epsilon. Okay. The next step is to clearly understand the dimension of each matrices. So we'll start with that. Y is equal to xw plus epsilon. Let us understand the dimensions. First thing is y. What is the dimension of y? See, whenever I'm telling you all these things, before I write the dimensions, try to think on your own and come up with the dimension. This is a very good exercise. It will really help you. Even if you get wrong answer in mind, when I tell the dimension, you'll be able to correct it and understand it in the perfect manner. What is the dimension of y? Think about it this way. You have n different data points, right? So for each of the n data points, you should be having different targets, y1, y2, y3, so on. And each of this target, I told you, is composed of what? Y1, y2, y3, and so on, right? There are multiple targets which composes each of those. So for each of the n data points, you have a m dimensional y. Let us consider this as m. That is, it is up to ym, y4, y5 up to ym. So you have n data points. For each of the data point, you have an m dimensional y, which means your matrix y is n by m matrix. Okay, this is an n by m matrix. So y matrix will look like this. It will have n different rows denoting n different data points, and each of this row will contain m features, that is y1, y2 up to ym. Understood? Okay. So y is an n by m matrix. N by m. Next is x. What is x? Your x is, think what should x be? Y is an n by m matrix. Now you have x. X also has n data points, right? If y is having n data points, obviously automatically x should also be of n data points. N data points is what it is coming from. N by what should be the dimension of x? The dimension of x should be, see, there should be n data points. This is the case of x. And each of the x, we'll consider it of p dimensions. Okay. Each of the x is composed of p dimensions, which means you have x1, x2, x3 up to xp. Okay. So p dimensional is the x. One thing you have to understand here is this won't be an n by p matrix. Instead, it will be n by p plus 1 matrix. Why is it p plus 1? Any thoughts? Because even though you have p different features which contribute to p dimensions, you need to add an extra dimension which is p plus 1, because this should be the intercept in your equation. That is, if you are simply writing a normal equation, let's say y is equal to w0 plus w1x1 plus w2x2 plus w3x3 plus so on. Here x1, x2, x3 are your features, but when you're writing equation, you have a term w0 where the value of x0, if you consider, is 1. Okay, let's say there is a w0 x0 here where x0 equal to 1. You can consider like that. In that case, w0 is the intercept in your equation, and in order to deal with this intercept, you should have one term in your matrix, and that matrix is a 1. So there are p different features which contribute to p dimensions. That is, each of these n data points will have p dimensions, plus you will have an extra dimension which is 1. So each of these rows first number will be 1. Then you will have other x1, x2 and so on. And that one I am denoting as p plus 1. Okay. I could have included this 1 in p. I specifically wrote it as p plus 1 so that you understand there is a first row which is a, first column which is a special column in x in which the values are all ones, and this is the because you have to deal with the intercept term w0. Okay. So now you have x matrix which is n by p plus 1 dimensional. The next one is w. What is w matrix? Your see, this thing is by, which is used for matrix. It's not an x. I just want to clarify. So y is n by m matrix, x is n by p plus 1 matrix. What is w? W should be, if you remember the equation that we wrote, for y1 there was w10, w11, w12, etc. For y2 we had w20, w21, w22, etc. Similarly for y3, y4 and so on. Which means how many rows should you have? You should have as many rows as you had in case of, and how many rows and columns should you have? This is the question. So you have m different values for y, right? There are m different values corresponding to each of the features in y, and there are p plus 1 different values corresponding to p features of x, and one is the intercept term, which is w0. So in total, this w matrix, it has to deal with p plus 1 different features. You should provide p plus 1 different w's, and for each of those there should be m different w's, which means w should be a p plus 1 cross m matrix. This is what w should be, which denotes p features of x and m targets or m features of y, that is m targets. So this is the dimension of w. And what is the dimension of epsilon? Epsilon, it is simply the number of data points, which would be n cross 1. So this is what you have to be very clear about. Only if you understand these dimensions very clearly, you will be able to have a hold on the derivation that we are going to do. The y matrix, it is n by m, which corresponds to n data points and m targets. Okay, for each of the data point, m targets. X is the matrix, which is n cross p plus 1, which corresponds to n data points for each of those p features. And what is p plus 1? For the intercept. And the w matrix, it is a p plus 1 by m matrix, in which there are p plus 1 corresponds to p features of x plus the intercept. And what is m? M is m different targets in case of y. And epsilon is an n by 1 matrix, in which corresponds to n different data points. So I'm going to erase this. Keep this very clearly in mind, because this is very important, the dimensions of each of the matrices. Okay, so let's start with the derivation. First thing is, we have to find the loss function or the error function. The error, we'll take it as the sum of squares error, as we took in univariate as well. So this will be sigma I is equal to 1 to n, corresponding to n different data points, yi minus xiw the whole square. So here I'm taking second L2 norm, and yi minus xiw the whole square. So this is another way of writing it like this. See, sigma I equal to 1 to n. Normally you can imagine like this. This would have been the initial equation, where you will have yi minus, what is xi? In place of xiw, you should actually be having w0 plus w1 xi1 plus w2 xi2 and so on. Okay, so instead of this, I am denoting this in the matrix form. Okay, and what is my yi and xi? Yi just means it has only the first row of the y matrix. We had seen y matrix was n cross m, right? Where n is the number of data points and m is the number of targets that you have. So for each of the n data points, you are going to calculate errors separately. So because of that, you are denoting it by yi. Yi is the one row. Out of these n rows, we are taking just one row, and each of those rows will be having m different features. Okay. Same is the case with xi. In case of xi, it is actually n cross p plus 1, out of which you are considering only the first row and p plus 1 vectors. That is what xi is. Okay. And w has all the rows, because it is applicable for x and y. So the next step is, as we did in case of univariate, we have to find the best w, or the best values of w in order to minimize this. How do you minimize the error? In order to minimize the error, you have to take the derivative with respect to w, that is dE by dw. This is what you have to take. You have to equate it to 0. This is how you will find values of w. So w is a matrix here. And in the same manner in which we did it for univariate in the previous lecture, we'll do for multivariate here. but all the operations will be matrix operations. Okay. So let us start with this. Let us take dE by dW. dE by dW. This can be written as, so this 2 will come outside, 2 times sigma I is equal to 1 to n, right? This will be y, I'll write it in yi minus xiw, right? xiw, here I left a space intentionally, xiw. So this 2 is already dealt with. Next is the term xiw. What is the derivative of minus xiw? It will be minus xi transpose. So that minus I am putting here and xi transpose I am putting here. So now the equation became minus 2 times sigma I equal to 1 to n xi transpose into yi minus xiw. And this should be equated to 0. This is how you have to equate derivative with respect to w to 0 and finally find the value of w. So let us solve this. I am going to convert this into totally matrix form. I am going to remove this summation sign. I just wrote summation separately so that you understand what terms we are summing. For each of the n, you have to take the sum. Okay. So if I take it totally into matrix form, it will become minus 2 into x transpose into y minus xw is equal to 0. This is what it becomes. So what did I do? Instead of taking summation, I took it as a single matrix. The whole matrix I took. So now x is a n by p plus 1 matrix. Y is a n by m matrix. Here it was x transpose, which will be the opposite, that is a p plus 1 by n matrix. X will be n by p plus 1 and w will be p plus 1 by m. Okay. So dE by dW is what we took. If I expand this, this will become minus 2 I can remove as we did in all the previous cases. If you divide by minus 2 in LHS and RHS, this will go away. So minus 2 I am erasing off. Now if I expand, this will become x transpose y minus x transpose xw is equal to 0. What is the next step? I have to take the term with w to one side and term without w to the other side because I have to find w. So x transpose x into w is equal to x transpose y. This is what I'll get. What is the next step? To find the value of w. W will become, if I take this x transpose x to the other side, it will become x transpose x whole inverse x transpose y, right? This is transpose. So this is the final derivation for the value of w. If you want to find the value of w, you have to do x transpose x whole inverse into x transpose y. Now let us understand, let us revisit the dimensions and see whether it matches up, because it should match up, then only the whole derivation works. So w is a matrix. What was w? It was a p plus 1 by m matrix, right? This is what our w was, and this equation should provide us w as the final answer. So how will you get it? X is a x is n by p plus 1 matrix. You agree with this? So what will be x transpose x? X transpose x will be p plus 1 by n multiplied by n by p plus 1. What will you get from this? If you multiply a p plus 1 by n matrix with an n by p plus 1 matrix, you will end up with p plus 1 by p plus 1 matrix, which means this will be p plus 1 by p plus 1 matrix. This will be x transpose x. What will be x transpose y? X transpose y, this will be x transpose y, x is n by p plus 1, which means x transpose is p plus 1 by n. So p plus 1 by n would be p plus 1 by n into what is y? Y is n by m. Okay. Now these two n's will cancel out. You will get p plus 1 by M matrix. So if you do X transpose X, it is P plus 1 by P plus 1. If you do X transpose Y, it is P plus 1 by M. Now if you take the inverse and do multiply this with this, what will you get? P plus 1 by M. So that is how you finally get W, which is P plus 1 by M matrix. So what is P plus 1 by M? W has P plus 1 rows, which denotes to P different features of X or the independent variable, along with one column, one row which has all ones, right? Which is corresponding to the intercept term. And what is M? M corresponds to the M different targets that you're having. So you finally found W, which is a P plus 1 by M matrix. So this is the derivation. So now you understood how to do derivation using matrices. In the previous lecture, what we had seen in case of univariate linear regression, and when I say univariate, in general it is that a single variable for a dependent variable. But when we did derivation, we had considered single variable for dependent variable and also single variable for the independent variable. That is how we had considered. And in case of multivariate, we have considered multiple variables for the dependent as well as multiple variables for the independent variable. So when we considered it, this is the most complex form in which we did derivation, and the previous linear regression, that is the easiest form, the simplest form. So now you know how to do it with variables and also with matrices, and you should be good to solve any linear regression problem from here on. In the next lecture, what we'll do is we'll take regularization into consideration and we'll do the derivation when regularization is there. Okay.